Chapter 9, Covalent Bonding Orbitals. In this chapter, we will talk about two topics, quite a bit about each topic. The topics are the HO model and the MO model. That stands for Hybrid Orbital Model and Molecular Orbital Model. Note that problem number 33 from the assigned homework only do parts A through E. In chapter 8, we discussed shapes of molecules. For example, looking at CH4, we would draw the Lewis structure, carbon surrounded by the 4 singly bonded hydrogens, and it would have the structure that is tetrahedral, bond angles of 109.5. In our picture, the one with the 109.5 degrees shown, that is showing hydrogen, the upper hydrogen and the carbon in the paper in your screen, and the hydrogens with the dashed bonds going back behind the screen, and the hydrogen with the dark triangular bond is coming out to give you a sense of what that looks like. Or follow the diagram B. Experiment shows us that it has a tetrahedral shape. All HCH bonds are 109.5 degrees. All 4 CH bonds are equivalent. That is, they have the same strength, they have the same length. So we have to keep that in mind as we discuss this. So now we'll discuss orbitals used for bondings. We have 2 models that we will work with. The hybrid orbital, HO model, we'll discuss that first. And we have the molecular orbital model, the MO model. Alrighty, so in our CH4 molecule, the carbon atom has the energy level diagram where we would have 2 electrons in the lower energy 1s atomic orbital, 2 electrons in the 2s atomic orbital, and 2 electrons in 2 of the 2p atomic orbitals. The valence electrons are the 2s and 2p electrons. Those are the ones involved in bonding. The 2 core electrons are the 1s electrons, and they are not involved in bonding. They are 2 within the atom to be on the outside enough to be involved in bonding. Okay, so we're dealing with CH4. So we have carbon, which we have then, just looking at the valence electron energy level diagram, we have the 2 paired electrons, the 2s paired electrons, and we have the 2 unpaired 2p electrons, unpaired given that they're in different atomic orbitals. So we might draw the electrons around the carbon atom where we put 2 together. Those would be the paired ones, and we separate the other 2. Those would be the unpaired electrons. We have 4 hydrogens, and each hydrogen has 1 1s electron. So we can picture hydrogen with an electron there, and 4 of them. Carbon cannot form 4 bonds since it only has 1 empty and 2 half-filled atomic orbitals ready for taking on more electrons in the formation of the CH4 molecule. So we take our picture, this one on the left, and what we do is we imagine as the molecule forms, there's lots of changes. We imagine one of the changes is that one of those 2s electrons is promoted up into a 2p atomic orbital. Now we have 4 half-filled atomic orbitals that we can imagine those hydrogen 1s electrons going into in an effort to make the molecule CH4. So a reminder of what the S and P atomic orbitals look like. The S atomic orbitals, if we imagine the nucleus and the core electrons in the middle of that XYZ axis, the S atomic orbital is a sphere. The P atomic orbitals are dumbbells with 2 lobes per atomic orbital, and they are oriented along the x-axis, we get px, the y-axis, we get py, and the z-axis, and we get the pz atomic orbital. Okay, now what we do is we imagine bringing in the hydrogen with each one with its 1s electron, and we put all those orbitals together, the S, the px, the py, the pz, we put them all together, one on top of the other. In the middle, in our diagram there, the one with the orange and the red and the green and the black, C in the center represents the core electrons and the nucleus of carbon. The smallest circle around the C is the 2s atomic orbital of it. Then we see the 2p atomic orbitals, the 3 of them. We see the px one is the green one, we see the py one is the red one, and we see the pz one is the orange one. So now what we do is we bring in the 1s atomic orbital. We bring in 4 of them because we have 4 hydrogens. The carbon has 4 electrons. Each hydrogen has 1. There's 4 hydrogens, so we have a total of 8 electrons. So if we bring in the hydrogen atomic orbital to the px, we overlap it with the green one, and we put those 2 electrons there. We do the same with the red 2p atomic orbital, the py one. We do the same with the pz atomic orbital, that's the orange one. Put the 2 electrons in there, and then our 4th 1s atomic orbital would overlap with the 2s orbital of carbon, and we put our 2 electrons in there. Okay, so as I wrote to the right of this diagram, to imagine bonds forming between the 4 hydrogen atoms and carbon, overlap the 1s atomic orbital on each hydrogen with an atomic orbital on carbon. The atomic orbitals on carbon, as we talked about a moment ago, are the 2s and the 3 2p atomic orbitals. So there's our picture, and this picture implies that there are 3 CH bonds that would be 90 degrees to each other. And we have then that 4th CH bond, which is composed of the 1s overlapping with the 2s atomic orbital. That would imply we have bond angles of like 90 degrees and something else. And we also would have 2 different types of bonds. This contradicts experimental data since it shows, that is the data, that CH4 has 4 equivalent bonds and they're at angles of 109.5 degrees. Okay, so that picture is too simple. So we have to go into a little bit more of a sophisticated model. A model, of course, is a man-made description of what's going on. We always try to keep it as simple as possible. If we find, nope, that doesn't quite work, then we add a little bit more to it. Okay, so our first model we will talk about is the hybrid orbital model, the HO model. Okay, so we're going to talk first about what's called sp3 hybridization. Alrighty, so looking at our carbon atom and how the electrons are distributed when we spread them all out to the 4 atomic orbitals, the 2s and the 3 2p's. Well, what we imagine is those atomic orbitals within the carbon atom hybridize together. They like blend together, and they come out giving us just what we need given the experimental data that we have, namely angles 109.5 degrees, all bonds between C and H being equivalent. That must mean that somehow the orbitals, as the molecule forms and bonds form from overlap of orbitals, somehow they must be equivalent. Okay, so we put then the 2s and the 2p atomic orbitals into our blender, and we come out with 4 new orbitals that we call hybrid orbitals, and their name, each one of them, is called an sp3 hybrid orbital. S because there's one s atomic orbital, p3 because there's 3 p atomic orbitals involved. So we start with 4 atomic orbitals, 2s plus 3 2b, and we end up with 4 hybrid orbitals. Hybridization of the s and px, py, and pz atomic orbital results in the formation of 4 identical sp3 hybrid orbitals. Each hybrid orbital has a large lobe and a small lobe, and the large lobes point toward the corners of a tetrahedron at angles of 109.5 degrees. So that's what we need to have our model match the experimental data. Okay, so this is showing those original atomic orbitals on the left side. They undergo that hybridization, and we get the 4 new hybrid orbitals that are shown in green. And those are oriented such that they would be along 109.5 degree angles relative to each other, and they contain, each hybrid orbital has 2 lobes, one big lobe and one little tiny lobe. And the big lobe is the one that provides a place for electrons to be, and it is the one that's oriented properly along the bond angles. So that picture on the far right, that is to show a tetrahedron with the 4 sp3 hybrid orbitals. The 1s atomic orbital on each hydrogen overlaps an sp3 hybrid orbital on carbon to form a bond. We need not alter the 1s atomic orbital on hydrogen since it does not contradict experimental results. So when we bring in hydrogen and its 1s atomic orbital, we just keep it a sphere because we can imagine a sphere overlapping nicely with any shape. Alrighty, so in the green and blue on the left there, we have a picture of what the CH4 molecule would look like, where the green balloons represent the hybrid orbitals on carbon. Their big lobe, the small lobes kind of get lost in the picture. And then the blue are the hydrogen's 1s atomic orbital. And you see where the atomic orbital overlaps with the hybrid orbital, we get a bond. That's where the 2 electrons are shown. The diagram to the right of that is showing a hand-drawn picture of CH4 showing the hybrid orbital sp3, the 4 of them, showing the 1s atomic orbital of the hydrogens. Where the orbitals overlap, we have a pair of electrons, and notice they have the paired spins, opposite spins, and okay, there's where we have bonds. So these bonds are covalent bonds. They're single bonds. They're composed of 2 electrons. They're also what we call sigma bonds. We would say CH4 has 4 sigma bonds. In a sigma bond, the pair of electrons is shared in the area centered on a line running between the nuclei. It's on the internuclear axis. So look at the sigma bond that is the topmost in the middle picture. So we have the pair of electrons between the hydrogen nucleus and the carbon nucleus, and that we term a sigma bond. Soon we will see another type of covalent bond that's called a pi bond. Whenever an atom in a molecule has 4 groups of electrons around it, they can be bonded pairs or lone pairs of electrons, it will adopt a set of 4 sp3 hybrid orbitals. So we have a table here that we will talk about each group of electron type. We're in the group of electrons 4, so we have 4 groups of electrons about the carbon atom. So we have hybrid orbitals quantity 4 of them, and they are type sp3. We have no atomic orbitals left over. Here's an example. Describe the bonding in NH3 using the hybrid orbital model. So what we would have to do is draw the Lewis structure, determine how many groups of electrons are about the atom, nitrogen, and we would see that there are 4 groups of electrons on nitrogen. Thus, we have 4 sp3 hybrid orbitals on nitrogen. The hydrogen continues with its 1s atomic orbital. Now, one of those 3 sp3 hybrid orbitals contains a pair of electrons. That's the lone pair. That's shown as the one on the top. The other places where the hydrogen atomic orbital overlaps with the hybrid orbital, we have sigma bonds. Again, we have the electrons between the nuclei, between the H and N. The picture in the green and the blue on the far right, that is to show that balloon type diagram. And again, we see that lone pair in the upper sp3 hybrid orbital. Okay, here's a problem for you to do working with water. Do that on your own. Okay, so that was sp3 hybridization. Now we're on the next type called sp2 hybridization. Take the molecule ethylene, which is that one there, C2H4. So that would be the Lewis structure of it. Carbon, each carbon has 1, 2, 3 groups of electrons around it. It would take on the trigonal planar shape about each carbon. The bond angles are 120 degrees. So we have something altogether different. Trigonal planar, not tetrahedral, 120 degree bond angles, not 109.5. So in our hybrid orbital model, what we do is we take the 2s and the 3 2p orbitals and we put them in the hybridization blender. Now, because we have only 3 groups of electrons on the carbon, we only need 3 hybrid orbitals. So we imagine taking the s and 2 of the p atomic orbitals to give us 3 sp2 hybrid orbitals. The 2p atomic orbital that was not affected is still there, it's still at the same energy value. Alrighty, so hybridization of the s and px and py atomic orbitals results in the formation of 3 sp2 hybrid orbitals. So here we have the p atomic orbitals and the s atomic orbitals that undergo hybridization to give us those 3 hybrid orbitals with the right angle 120 degrees. The diagram on the left shows us the picture with carbon in the center and the 3 sp2 hybrid orbitals shown in green, the unaffected p atomic orbital shown in orange. Of course, you recall that that's one orbital with 2 lobes, that p atomic orbital. So now we put it together. We put the 2 carbons together. We put the 4 hydrogens in our picture. And we come up with this middle diagram with the blue and the green. Consider the C and 2 hydrogens on the left in the diagram. The 1s atomic orbital on each hydrogen overlaps with 2 sp2 hybrid orbitals on carbon, and the third sp2 hybrid orbital on carbon overlaps with an sp2 hybrid orbital on the other carbon to make all of them sigma bonds. So this diagram here is just looking at the hybrid orbitals and the 1s atomic orbital on the hydrogen. So notice that we bring in those 4 hydrogens, 2 on each carbon. We get 2 sigma bonds from those. And then we have to bring the carbons together and we get a sigma bond there. So we're showing 5 sigma bonds, and 4 of them, those involving hydrogens, are a 1s sp2 overlap kind of sigma bond. The middle sigma bond is an sp2 sp2 overlap sigma bond. They're all sigma bonds because the electron pair, the bonded electron pair, is between the nuclei. The third diagram is getting back to those p atomic orbitals, those original unaffected ones. Each carbon has a p atomic orbital. And what we imagine in this model is those p atomic orbitals, they overlap each other. They, kind of like the picture shows, they have a region above the nuclei and a region below the nuclei where a pair of electrons, a bonded pair of electrons, can be. That bond is called a pi bond, and it is made by the side-by-side or the parallel overlap of the atomic orbitals. So it is parallel or side-by-side. That's a pi bond. Electrons are above and below the nuclei, whereas a sigma bond is a head-on overlap of the orbitals, and the electrons are right between the nuclei. Putting that all together in a picture, we have this diagram here on the left, diagram A. It's showing the hydrogens, the sigma bonds. It's describing the names of all the orbitals. We have the 1s orbitals on hydrogens. We have the 3 sp2 hybrid orbitals on each carbon, and then we have a 2p atomic orbital on each carbon. So depending on how they overlap, whether head-on, we get sigma, or side-by-side, we get pi. And that allows for the double bond. So within a double bond, one bond is a sigma bond, one bond is a pi bond. The pi bond is electrons above, below, the sigma bond, electrons between. So we would say ethylene or ethene has 5 sigma bonds and 1 pi bond. Due to the pi bond, the carbon atoms cannot rotate about the CC bond, since for the pi bond to exist, the p atomic orbitals on each carbon must be parallel. So we have sigma bonds can rotate, pi bonds cannot. Whenever an atom is surrounded by 3 groups of electrons, bonding or lone pairs, a set of 3 sp2 hybrid orbitals form. Okay, so now we have covered groups of electrons, the 3 and the 4. Notice in line 3, we have the hybrid orbital, 3 of them, type sp2, and then we do have 1 atomic orbital, a p or a 2p atomic orbital left over, and that's part of the pi bonding. Alrighty, so now we will get into the 2 groups of electrons category, and that gives rise to what's called sp hybridization. that occurs on the carbon atom within CO2. So there's the Lewis structure for CO2. We have on carbon two groups of electrons. So we have the linear shape, and we have the bond angle of 180 degrees. And the last picture in that table is showing the original valence electron, atomic orbitals, and then after hybridization we get two sp hybrid orbitals, and we have the original 2p hybrid orbitals still there. Those two are going to be involved in pi bonding. Okay, so that next diagram shows the original atomic orbitals, hybridization, and where those orbitals are. Those hybrid orbitals. Okay, so now we have this picture on the left where we're seeing the two sp hybrid orbitals. They're 180 degrees apart from each other, and they're the green ones. We also see the p atomic orbitals. We have the vertical one, and we have the one going into the board and coming out of the board, the plane, your screen, and those are p atomic orbitals. So in this diagram with the green and the kind of olive color, carbon in the middle, now we've got the oxygen. On the carbon we have the hybrid orbitals sp. The p atomic orbitals are for the moment left off. On oxygen we have three groups of electrons. Let's go back to our Lewis structure. On oxygen, we have 1, 2, 3 groups of electrons. So we know whenever there's 3 groups of electrons, the hybrid orbitals used are sp2, and there's 3 of them. So those are shown in the olive color for each of the oxygen atoms. And they are at the angles 120 degrees. There's 3 of them. 2 of those sp2 hybrid orbitals just contain lone pairs. It's the sp2 hybrid orbital that overlaps with the sp hybrid orbital on carbon that gives us the sigma bond between the O and the C. Alrighty, so 2 p atomic orbitals remain unhybridized on C, and there's also a p atomic orbital on each oxygen. So the p atomic orbitals on carbon are perpendicular to the internuclear axis. So that's in our diagram here. We have oxygen, it's showing its p atomic orbital and its 3 sp2 hybrid orbitals. The diagram on the right side, we show carbon in the middle with its hybrid orbitals, and they're shown in that green color, and then we have with orange the 2 p atomic orbitals on it, 90 degrees from each other. So there we have a lot of information, and we get pi bonds between the C and the O by overlapping the p atomic orbitals on C with those on O that are parallel to each other. So we have the pi bond on the left side, we have the pi bond on the right side, and that would be the total hybrid orbital bonding picture of CO2. So there are 2 sigma bonds in CO2, and there are 2 pi bonds in CO2. The summary of this is whenever an atom is surrounded by 2 groups of electrons, bonding or lone pairs, a set of sp hybrid orbitals forms, a set of 2 sp hybrid orbitals. So now we've completed our table, 2 groups of electrons on the atom. We have sp type hybrid orbitals, we have 2 of them. And for atomic orbitals, we have p atomic orbitals, and we have 2 of those. Here are some examples for you to look at. And the solutions are right there. We won't go over them now. I will want you to go back and take a look at them yourself. Here is another problem involving cholesterol, which is that shown in what we call line structure there. And the answer to this one is in the back of these notes. Alrighty, so for the 2 covalent bonding models that we have, we've talked about the hybrid orbital model. It could also be called the localized electron model. The electrons are localized in that region of overlap of the orbitals. It's localized. The electrons do not have access to the entire molecule. They have access just to what they are connecting. Okay, it turns out it might not feel like it to you now, but for us chemists, it's easy to use. It addresses geometry well. It supports the lack of rotation about the double and, if there were, triple bonds. So whenever there's more than a sigma bond, that is a double or triple bond, those atoms cannot rotate around relative to each other. The molecular orbital model, that's one that we will now talk about. It addresses bond strength, that is how strong bonds are. And it turns out we'll talk about something called bond order. As the bond order increases, that means for us the bond strength increases. It also addresses magnetism. Why are some molecules magnetic? It addresses that. The hybrid orbital model does not. So, liquid oxygen turns out to be magnetic. What we have is, in that picture, we have a strong magnet, the typical kind of round magnet. Those are the North Pole, the South Pole. We have in the upper left of the diagram, we have a beaker containing liquid oxygen that's being poured between the poles of this magnet. And the liquid oxygen is sticking between the north and south poles until it evaporates. So, oxygen is magnetic, and we will learn why when we study this molecular orbital model. The molecular orbital model can be used on molecules and ions with an even or an odd number of electrons. For example, it can be used with NO, which has 11 valence electrons. The hybrid orbital model does not address odd electron molecules. Okay, so the molecular orbital model offers a lot more, which means it's a little more complicated, definitely. But we will see a little bit of ideas of what's behind the theory of it, but mainly we'll just see how to work with it. And then if you go on and study more chemistry, you will get more into the theory of it. So the molecular orbital model, it involves quantum mechanics. And quantum mechanics involves waves, namely electron waves. Remember chapter 7 and atomic orbitals having to do with describing regions where electrons can be found, but also having to do with the wave nature of electrons. Okay, so let's go back for a quick review of waves. Oops. So these are showing the diagram on the left, constructive interference, the diagram on the right, destructive interference. So what we have for waves that are in phase, we have that pink wave, which is cresting at about 2 and about 8, and then we have the wave below it shown in blue cresting at about the same spots. Well, if those 2 waves were to overlap, they would make for a super wave. They would add, and we would have what we call constructive interference. If we have the waves out of phase, so the pink is cresting where the blue is troughing. When they interact, when we add them together, what they do is they cancel each other out. We get destructive interference. In the molecular orbital model, atomic orbitals come together and form molecular orbitals. Molecular orbitals, like atomic orbitals, describe locations where electrons can be found. Just as wave functions are used to describe atomic orbitals, wave functions are used to describe molecular orbitals. Okay, so waves, and that's why we had that little review of waves, enters into this. We won't really deal with it too much. We will just deal with kind of the outcomes of waves interacting. One more thing about molecular orbitals is they are not localized between, or they're not localized about particular nuclei. They are really about the whole molecule. So we say that molecular orbitals are delocalized over the entire molecule. And the picture there, I try to describe that. In the hybrid orbital model, we imagine orbitals overlapping. The region of overlap is where the electrons are in a sigma kind of overlap. And that's very localized between the two nuclei. When we have the MO model, and those black spots are representing the nuclei and any core electrons, we have an MO that goes about basically the entire molecule, and electrons can be then anywhere within that region of overlap. That not overlap, just that MO space. When two atomic orbitals constructively interfere, a bonding MO results. A bonding MO favors bond formation. When two atomic orbitals destructively interfere, trough to crest, we get what we call an anti-bonding molecular orbital, destructive interference. An anti-bonding MO opposes bond formation. Both bonding MO and anti-bonding MOs are possible because of the wave properties of the electron. Okay, so I try to show that with these pictures here. Bonding and anti-bonding MOs. So we're on the left side of this table. Go to the picture on the bottom. The in-phase electrons exist between nuclei. So when we have two different atoms coming together, and their s, because these are spherical here, their s atomic orbitals have the same phase, both cresting at the same spot, for example. We would give that a positive association, a positive sign association. When they both crest at the same point, we get constructive interference, we get a bonding MO, we get a space about those nuclei where electrons can be found that favors bond formation. Now go to the upper picture. If those nuclei are coming together, but they're out of phase, we have a plus in one case, a minus in the other, they're going to lead to destructive interference. They will lead to an MO that is what we call an antibonding MO. It does not favor bond formation. It disfavors bond formation. Notice that we have electrons, we have the MO. That MO is just one MO. It's got the two parts to it. The main parts of that MO are on the outside of the nuclei. And that means that it's not favoring bond formation. It's not bringing those nuclei together. Both of these MOs, the one called MO1, the bonding MO, and the one called MO2, the anti-bonding MO, both of these are sigma MOs because they come about from the head-on overlap of orbitals, of atomic orbitals. Going to the right part of the table, we have an energy level diagram. We have, let's say this is for the molecule H2. So we have atom A, the one on the left, we have atom B, the one on the right. So those are the original unreacted, uncombined atoms, and we're seeing their 1s electron. Well, depending on how they interact, we get either the MO1, which is the bonding MO, that favors bond formation. That means that if we're looking at energy, the energy of that MO is lower than the original atomic orbital energies. And we also get, from a destructive interaction kind of effect, we get MO2, and that disfavors bond formation. So that means we can picture it as electrons have to go to higher energy to occupy that state. That is not favoring bond formation. It is, in fact, disfavoring. So now we're going to get into more details of the MOs. Labels on the MOs indicate their shape, the parent atomic orbitals they came from, and whether they are bonding or anti-bonding. If an anti-bonding MO, we put an asterisk on it. MO electron configuration is written in the same way as the atomic orbital electron configuration we learned about in chapter 7. Each MO can hold up to 2 electrons. They have spins that are opposite. Same idea with the atomic orbitals. MOs are conserved. That is, there are as many MOs made as there were atomic orbitals to construct them. All right, so this table here shows energy level diagrams, and this is for the one on the left. We've talked about that. We have 2 atoms involved, atom A, atom B, and if they have just S atomic orbitals involved, like we're talking H2 or maybe He2, the energy level diagram would look like that. The second diagram there specifically is for H2, the molecule, starting with 2 separate H atoms with their 1s electron. And then we draw the MO energy level diagram between the atomic orbitals, and the lower energy MO, the bonding MO, has the name sigma 1s. Sigma because it's a head-on overlap of those 1s atomic orbitals, and it is made of 1s atomic orbitals, so it's called sigma 1s. We will see we have sigma 2s. We have sigma 2p atomic orbitals. We'll get into those later. The upper energy atomic orbital, or the upper energy MO, is the antibonding one, and that is called sigma 1s star. So we take those 2 electrons, we put them into the lower energy MO, the sigma 1s MO, and we get the MO electron configuration sigma 1s2. The third diagram in this table is if we had 1 more electron. Let's say instead of having H2, we have H2 minus. Now we have a total of 3 electrons. So we place 2 in the lower energy MO, the sigma 1s MO, and the third one in the higher energy MO, the sigma 1s star MO. So the electron configuration would be sigma 1s2, sigma 1s star 1. Our last diagram is the energy level diagram for He2. Now we have a total of 4 electrons to deal with. So we have 2 in the sigma 1s MO, and we have 2 in the sigma 1s star MO. So the energy electron configuration for He2 would be sigma 1s2, sigma 1s star 2. Next, we will talk about bond order. It is a measure of the bond strength. As the bond order increases, bond strength increases and bond length decreases. When the bond order is 0, there is no bond. Bond order is the number of bonding electrons the total number of bonding electrons, minus the number of antibonding electrons, the total number of antibonding electrons, all divided by 2. For example, calculate the bond order of H2, H2 minus, and He2. Okay, so what we have to do is go back to the diagrams. Here's the diagram. The second one is the diagram for H2. So we have 2 sigma 1s electrons. And we have, let's go back up here, we have no antibonding electrons. So we have 2 bonding electrons, and we have no antibonding electrons. So we have 2 minus 0 divided by 2. Bond order is 1. That would correspond to a single bond, which is what we see in H2. Okay, now looking at H2 minus, here's its energy level diagram, the third one there. We have 2 bonding electrons. We have 1 antibonding electron. So we have bond order equals 2 minus 1 over 2. It is a half. Now, that's a smaller number than the bond order for H2. What that means is that H2 minus, its bond, it exists because it's not 0, but it is weaker than the H2 bond. For He2, we have, according to that last diagram, we have 2 bonding electrons, we have 2 antibonding electrons. So our bond order is 2 minus 2, 0 over 2, 0. So He2, it does not exist. But if we removed one of those antibonding electrons, so we have He2 plus, it could exist because it has 1 less unfavorable or antibonding electron. Okay, so we considered how s orbitals interact. Now we'll consider how p orbitals interact. And we will look at homonuclear diatomics. That means we have 2 atoms involved, homonuclear meaning they're the same, like B2, C2, and so forth, N2. We will look first at boron, 2 boron atoms together. Each boron atom has the electron configuration 1s2, 2s2, 2p1. So for valence electrons, we have s1s and we have p1s. So we have to consider p atomic orbitals. So in this table here, what we have is just the p atomic orbital consideration. The s atomic orbital stuff we have dealt with above, and we'll blend that together once we get the p orbital stuff dealt with. Alrighty, so on each boron atom, that's A, we have the pz, py, and px atomic orbitals. Notice their signs for the lobes. Each orbital has a plus lobe and a minus lobe. They're oriented along the 3 axes. So the vertical ones that interact, they form a pi type MO. And that's shown in diagram B. The diagram C shows the ones with the lobes going into the screen, coming out of the screen. So they're parallel. So both B and C orbital interactions make for pi MOs because of their side-by-side or parallel interaction. The last interaction is the one shown in D. They interact, and they are interacting in a head-on sort of fashion, so they make a sigma MO. Sigma MOs allow for a better interaction, so they are lower in energy in general than the pi interaction MOs. Alrighty, so here's another hand-drawn picture of this. What we have is the original atomic orbitals, the p atomic orbitals. We're just considering p atomic orbitals right now. So we have the original ones on the two separate atoms, like imagine the boron atoms, and then they come together, and depending on what kind of interaction they have, they form sigma 2p MOs. They have the low energy bonding one, and then the very high energy anti-bonding one. That's called sigma 2p star. Notice that as much as the one favors bond formation, the other one disfavors bond formation. So it goes to as high an energy position from the original energies as the other one goes down. So, and then the remaining pi MOs are shown there in the middle. Remember that there are two of each one. So depending on if they're favorably interacting, we get pi 2p, two of them, or unfavorably, we get pi 2p star. And the hand-drawn pictures on the right are showing you those favorable or unfavorable. In this hand-drawn picture, instead of putting pluses and minuses, we have the dashed or the not dashed lobes. Okay, so now we have a diagram from your textbook, the energy level diagram for boron, showing the S MOs, the sigma 2s, sigma 2s star MOs, along with the P MOs, the sigma 2p, the pi 2p's, pi 2p star, and the sigma 2p star. So notice how they go up in energy. So with boron, each one has 3 electrons, so we have a total of 6. So we fill those 6 in the middle on the MO portion, putting 2 in the bottom, and then 2 above, and then 2 in yet one above. So that would be the expected MO energy level diagram for B2. Okay, now we'll talk about magnetism. A diamagnetic compound contains only paired electrons. It is weakly repelled by a magnetic field. It is hardly affected by a magnetic field. So a diamagnetic compound contains only paired electrons, and it won't behave as oxygen did in that magnetic field. B2, if this is the correct energy level diagram, it's got all paired electrons. We would expect it to be diamagnetic. A paramagnetic compound contains at least one unpaired electron. It's attracted to a magnetic field. There's a third category called a ferromagnetic compound, and it also contains at least one unpaired electron, and it can be made to be a permanent magnet. The paramagnetic compounds are attracted to a magnetic field in the presence of one, but otherwise do not behave as a magnet. All right, so this diagram with the red balls shows the 3 different situations. Go to the middle one, paramagnetic. They have at least one unpaired electron, so that each one of those circles with the arrow through it, that arrow is meant to be that unpaired electron. It makes for a little mini magnet. And when we have no magnetic field, that is H is 0, they're all randomly oriented. But as soon as we have a magnetic field, they get lined up with the field. In a diamagnetic compound, our circles are empty because we don't have any little mini magnets. Ferromagnetic doesn't matter whether the field is on or off. We always have it behaving magnetically. So, oxygen poured into the space between the magnet, as we talked about before. Oxygen, O2, turns out to be paramagnetic. It has at least one unpaired electron. This diagram here, this one on the right, the valence with the electromagnet, that is meant to describe how we measure paramagnetism or diamagnetism, for that matter. We put the sample in, that's in this pink region. We put it between the poles of a magnet. Oh, before we put it between the poles of the magnet, we weigh it. Then we bring in the poles of the magnet, so it's between a magnet. If it's diamagnetic, its mass doesn't really change. If it's paramagnetic, it gets drawn more into the magnetic field and its mass goes up. Alrighty, so as we talked about, B2 is predicted to be diamagnetic. Turns out it's paramagnetic. That's what experiment shows us. So what we have to do is modify our model a little bit. It turns out that the energy level diagram for B2 and also for C2 and N2 looks like the one shown here. So it turns out that the sigma 2p MO energy goes up, making electrons in that MO be put there after ones are put in the pi 2p MO. And on the right in that table, I try to give an explanation of why this would be the correct energy level diagram for B2. So if we have this, which is the correct one, if this is the correct MO energy level diagram, what we have are two unpaired electrons. That is, B2 is now predicted to be paramagnetic, which it is experimentally. So for molecules like C2, like N2, they have this energy level diagram. For molecules like O2 and F2, they have the energy level diagram that was that first one that we came up with. And that's all summarized here. So here are energy level diagrams for B2, C2, N2. Those three, their energy level diagrams look the same. Of course, the different numbers of electrons we put in depending on how many the molecule has. For O2 and F2, those are the original energy level diagrams. So notice the difference. The one goes sigma 2s, sigma 2s star, pi 2p, sigma 2p, pi 2p star, sigma 2p star. That would be what we have for B2, C2, and N2. For O2 and F2, it goes sigma 2s, sigma 2s star, sigma 2p, then pi 2p, then pi 2p star, then sigma 2p star. So check those out and make sure that you could come up with those with the number of electrons we have in each of those molecules. Notice that O2 does have unpaired electrons, so we would expect it to be paramagnetic. F2 does not, N2 does not, C2 does not. Those would all be diamagnetic. B2, also unpaired electrons. Calculate from each of these the bond orders. Make sure that you agree with those numbers. And then we have the observed bond dissociation energy. So the bigger is the bond order, the larger we expect the bond dissociation energies to be, and they roughly follow. And then the bond length. If we have a big bond order, the nuclei are far apart, and so we expect a big length. Smaller bond order, or bigger bond order, closer nuclei, we expect a smaller observed bond length. So there are now some examples for you to do, and our next section is heteronuclear diatomics. So those are ones that have two different atoms involved. They're diatomic, so just two atoms, two different ones. So it could be NO, could be CO, and any ions thereof. Alrighty, so we have our two energy level diagrams that we will consider. We have that the one that works for heteronuclear diatomics like CO, NO, that's the one for B2, for C2, for N2. And then pretty much that second one, the original one that we came up with, that pretty much only works for O2 and F2. If you have to work with Ne2, use that one. Okay, so we have another example, and then we're done with this chapter. So, as always, go over these notes as much as you need to. Read through the chapter 9 in your textbook, do the assigned homework problems, get on that quiz when it opens, and then you have an exercise and perhaps an experiment to do on this topic, but I'll be informing you about those in my announcements to you.